Poiseuille's equation. What is Poiseuille's equation? Here you have a burette connected to a capillary tube. The burette is filled with a liquid, and this liquid flows through this capillary tube and it is collected in the beaker. Poiseuille's equation explains how a liquid flows through a narrow pipe or capillary tube under steady, smooth conditions. Poiseuille's equation tells us how the volume of liquid flowing per second depends on the volume of liquid flowing per second. First, it depends on the liquid's viscosity eta. Second, it depends on the radius of the capillary tube r. Third, it depends upon the length of the capillary tube L. And fourth, it depends upon the pressure difference P across the tube. The left hand side, the pressure is H rho g. The right hand side, the pressure is 0. So the pressure difference del P is H rho g minus 0, which is equals H rho g. We take this del P as P here. Assumptions for Poiseuille's equation. Before deriving the equation, we assume 1. Flow is streamlined, smooth, not turbulent. 2. The tube is horizontal, no effect of gravity. 3. Liquid layer touching the tube wall is at rest, no slip condition. 4. Pressure is uniform across any cross section of the tube. All these 4 conditions has to be assumed to derive the Poiseuille's equation. 1. The flow is streamlined, the tube is horizontal, the liquid layer touching the wall of the tube is at rest, the pressure is uniform across any cross section of the tube. Dimensional analysis to derive the formula. Consider a liquid flowing steadily through a horizontal capillary tube. Let V be the volume of the liquid flowing out per second. V upon T equals the dimension of this small v is L cube T power minus 1. The small v, the volume of the liquid flowing out per second, depends on 1. Eta, the coefficient viscosity of the fluid or liquid. The dimensional formula of eta is m L power minus 1 T power minus 1. Then the v depends upon r, the radius of the tube. The dimensional formula is simply L. Third, the v depends upon the pressure gradient P upon L. More is the length, then to maintain the same rate of flow, we have to increase the pressure. So P by L is constant. The dimensional formula of P by L, m L power minus 2 T power minus 2. So V proportional to eta power A, R power B, P by L to the power C. Let us bring a constant to have a perfect equation. So V equals K times eta power A, R power B, P by L to the power C. K is a proportionality constant. Let us substitute the dimensional formula for each quantity. For volume flowing per second, it is L cube T power minus 1. For eta, the dimensional formula is m L power minus 1 T power minus 1. And for radius, the dimensional formula is L. And for P by L, the pressure gradient, the dimensional formula is m L power minus 2 T power minus 2. Now, let us bring all m term together, L term together and T term together. So we get m power A plus C, L power minus A plus B minus 2C, T power minus A minus 2C. So let us bring the m power 0 on the left hand side. Let us equate the power of m on both sides. We get A plus C equals 0. Next, let us equate the power of T term. So we get minus A minus 2C equals minus 1. When we add these two equations, A minus A is getting cancelled. then we get minus C equals minus 1. So C equals 1. Good. Substituting C equals 1 in the first equation, we get A plus 1 equals 0. So A equals minus 1. Now, let us compare the power of L. So, we get minus A plus B minus 2C equals 3. Let us substitute the value of A is minus 1 and the C as plus 1. So, we get minus 1 of minus 1 plus B minus 2 times 1 equals 3. On simplifying this, we get B equals 4. On solving, A equals minus 1, B equals 4 and C equals 1. Therefore, the equation become B equals K times eta power minus 1 R power 4 P by L to the power 1. Experimentally, we found that the value of K is pi upon 8. Therefore, the volume of liquid flowing out per second small v equals pi R power 4 P divided by 8 times eta L. This is the final formula of Poiseuille's equation. Using dimensional analysis, we got it. That's it. This is Poiseuille's equation, a powerful tool to understand how liquids behave in thin tubes like blood in veins or oil in pipelines.